Hello, friend. Welcome to Science for Sleep. Whether you have returned tonight or you are finding this quiet corner for the first time, this is a gentle place to slow down, learn something soft and steady, and let the day gradually loosen its hold. Tonight, we are looking at metabolism. That word can feel strangely personal. Some people hear it and think of a fast metabolism, a slow metabolism, body fat, hunger, aging, fasting, exercise, or the quiet question of why one body seems to burn energy differently than another. But metabolism is not one tiny furnace hidden somewhere inside you. It is not only the speed at which you burn calories, it is the total chemical work of staying alive. Even now, while the body is still, thousands of small tasks are continuing without needing attention. The heart keeps squeezing blood through arteries and veins. The lungs keep moving air in and out. The kidneys keep filtering the blood, sorting water, salt, acids, and waste. The liver keeps adjusting the chemistry of the bloodstream, storing some nutrients, releasing others, and making proteins the body needs. The brain keeps sending electrical signals through nerve cells, even in sleep. And every one of these quiet jobs requires energy. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find this calm corner of science, one sleepy listener at a time. The energy used by a resting body is often called basal metabolic rate or resting metabolic rate. In simple terms, it means the energy the body uses before deliberate exercise is added, before a walk, before a workout, before climbing stairs, lifting bags, or cleaning a room. It is the cost of simply keeping the body running. For many adults, this resting work makes up the largest part of daily energy use. That can be surprising, because exercise is easier to picture. A person can see a jog, a bike ride, or a set of weights. It is harder to picture a liver cell making glucose during the night, or a kidney cell moving sodium across a tiny membrane, or a brain cell holding an electrical charge so a signal can pass. But those hidden processes are metabolism too. At the center of this work is a molecule called ATP. Its full name is adenosine triphosphate, but the simple idea matters more than the long name. ATP is like the body's small usable energy packet. Cells do not usually take a bite of food and use it directly. They take energy from food or from stored fuel and transfer part of that energy into ATP. Then ATP can power very specific jobs. It can help a muscle fiber contract. It can help a nerve cell send a signal. It can help a cell build a protein, repair damage, move minerals, copy instructions, or maintain its shape. This is why metabolism never truly turns off. A sleeping body is quieter than a running body, but it is not inactive. Its temperature is still being controlled near 37 degrees Celsius. Its heart may slow, but it does not stop working. Its breathing may become gentle and regular, but oxygen is still moving into the blood, and carbon dioxide is still leaving. Cells are still using fuel. Heat is still being produced. Tissue is still being repaired. Hormones are still rising and falling in time patterns. This is also why the phrase fast or slow metabolism is useful, but incomplete. it points towards something real. Bodies do differ. One person may burn more total energy in a day than another. One person may store fat more easily under the same conditions. One person may feel hungry sooner, move more without noticing, carry more muscle, have different hormone signals, or respond differently to sleep loss, fasting, stress, age, or temperature. But those differences do not come from one simple dial. They come from organs, cells, hormones, muscles, fan tissue, digestion, movement, and the quiet chemistry inside mitochondria, the small structures in cells that help turn fuel into usable energy. So the question is not only whether a metabolism is fast or slow. The deeper question is what the body is doing with energy, where it sends it, where it stores it, when it releases it, and why two bodies can make different choices from the same basic materials. To understand that, it helps to begin with food itself. Because food is not truly body fuel the moment it reaches the mouth. It first has to be taken apart, softened, split, absorbed, carried, sorted, stored, and transformed. A meal begins its quiet change before it reaches the stomach. The first work happens in the mouth, where teeth crush food into smaller pieces and saliva wets the surface. Saliva contains an enzyme called amylase, which begins breaking some starches into shorter sugar chains. A bite of bread, rice, potato, or pasta is already starting to change before it is swallowed. The tongue shapes the softened food into a small rounded mass called a bolus, and the throat guides it down the esophagus. From there, smooth muscle squeezes in a wave-like motion called peristalsis. This same basic motion moves food through much of the digestive tract, slowly and steadily, without needing conscious control. When food reaches the stomach, it enters a strong, muscular pouch that can hold and mix a meal for several hours. The stomach releases hydrochloric acid, a sharp acid that often brings the stomach's pH down near 1 to 3. That acid helps unfold proteins, making them easier for enzymes to cut apart. It also kills many microbes that arrive with food, though some are able to survive the trip. The stomach also releases pepsin, an enzyme that begins cutting proteins into smaller pieces. A scrambled egg, a piece of chicken, lentils, yogurt, or beans all contain proteins made of long chains. Those chains have to be clipped down into amino acids, the smaller building blocks the body can absorb and reuse. The stomach does some of this work, but much of digestion happens after the partly mixed food moves into the small intestine. The first part of the small intestine is called the duodenum. It is only about 25 centimeters long, but it receives some of the body's most important digestive fluids. The pancreas sends in enzymes through small ducts. Pancreatic amylase continues breaking starches towards simple sugars. Proteases from the pancreas cut protein pieces into shorter chains and amino acids. Pancreatic lipase helps break fats into fatty acids and glycerol. These names sound technical, but the basic action is simple. Large food molecules are being cut into pieces small enough to pass into the body. Fat needs extra help because it does not mix easily with watery digestive fluid. The liver makes bile, a greenish-yellow fluid that helps handle fat. Bile is stored and concentrated in the gallbladder, a small pouch tucked under the liver. When a meal contains fat, The gallbladder squeezes bile into the small intestine. Bile acts a little like soap in water. It breaks large fat droplets into much smaller droplets, giving enzymes more surface to work on. A spoonful of olive oil, the fat in salmon, butter on toast, or the fat inside an avocado, all need this kind of mixing before they can be absorbed well. Carbohydrates, proteins, and fats then move along separate chemical paths. Carbohydrates are reduced mostly to simple sugars, especially glucose. Glucose is one of the body's most important blood sugars because many cells can use it quickly. Proteins become amino acids, which can help build muscle fibers, enzymes, immune proteins, skin, hair, and many other body parts. Fats become fatty acids and glycerol, which can be used for cell membranes, hormones, energy, and long-term fuel storage. Absorption is physical work as much as chemical work. The adult small intestine is roughly 6 meters long, but its real absorbing power comes from its inner surface. That surface is folded and covered with tiny finger-like projections called villi. Each villus is covered with even smaller projections called microvilli. Together, these folds and projections create a wide living surface where digested nutrients can cross into the body. Glucose and amino acids usually pass through the wall of the small intestine into tiny blood vessels. From there, they travel through a large vessel called the portal vein, which carries nutrient-rich blood directly to the liver. The liver sees many absorbed nutrients early and helps sort, store, release, or change them. Many fats take a different route. After fatty acids and glycerol are absorbed into intestinal cells, many are rebuilt into triglycerides and packed into small transport particles called chylomicrons. These particles are too large to enter ordinary blood capillaries right away. They first move into tiny lymph vessels called lacteals, then travel through the lymph system before entering the main bloodstream near the upper chest. By the time a meal has passed through this first hidden journey, it no longer resembles the food on the plate. Its starches, proteins, and fats have become sugars, amino acids, fatty acids, glycerol, and transport particles. Now the body has a new task. These molecules have arrived, and the body must decide what to use right away, what to store for the next few hours, and what to save for much later. The first strong signal after many meals comes from a small organ behind the stomach. The pancreas sits deep in the upper abdomen, close to the first curve of the small intestine. Inside it are tiny clusters of hormone-making cells called pancreatic islets. Some of those cells are beta cells, and beta cells make insulin. When glucose from a meal rises in the blood, insulin helps tell many tissues that fuel is available. Muscle cells, fat cells, and other insulin-sensitive tissues respond by moving more glucose transporters to their surfaces. A transporter is a small protein doorway that lets a substance cross a cell membrane. With more of these doorways available, glucose can leave the blood and enter cells more easily. Inside a cell, glucose can be used to help make ATP, the small energy packet that powers cellular work. A muscle fiber may use glucose to contract. A liver cell may use it to carry out chemical processing. A fat cell may use part of it, while also preparing to store extra energy. The body also has a short-term storage plan for glucose. That stored form is called glycogen. Glycogen is made of many glucose units linked together in a branching structure, almost like a tiny tree made from sugar. The liver stores glycogen, so it can help steady blood glucose between meals. During the night, when no food is being absorbed, the liver can break some glycogen back into glucose and release it into the blood. This is one reason blood sugar does not normally fall to zero during sleep. Muscles store glycogen too, but muscle glycogen mostly stays inside the muscle that made it. A calf muscle cannot simply donate its stored glycogen to the brain. A thigh muscle stores that carbohydrate for its own contractions during walking, climbing stairs, running, lifting, or even standing upright. This short-term storage system is useful, but limited. Glycogen holds water along with it, and the body can only store so much. Long-term energy storage uses a different system. That system is body fat. The main stored form of body fat is called a triglyceride. A triglyceride has one glycerol backbone with 3 fatty acids attached to it. Those fatty acids are long carbon-rich chains, and their chemical bonds hold a lot of usable energy. Fat stores more energy per gram than carbohydrate or protein. Carbohydrate and protein each provide about 4 calories per gram. Fat provides about 9 calories per gram. That difference matters because a body that had to store all long-term energy as wet glycogen would become much heavier and bulkier. Fat gives the body a compact way to save energy for later. The cells that specialize in this storage are called adipocytes. An adipocyte can hold a large droplet of triglyceride inside it. Under a microscope, a white fat cell often looks like a clear round bubble, with its nucleus pushed toward the edge. That shape comes from the fat droplet taking up most of the cell's inner space. After a meal, insulin encourages storage when energy is available. It helps glucose move into cells. It supports glycogen building in the liver and muscles. It also makes it easier for fat cells to store fatty acids as triglycerides. Some fatty acids arrive after being absorbed from food. Under certain conditions, the liver can also convert extra carbohydrate into fat through a process called de novo lipogenesis, which means making new fat. In humans eating ordinary mixed diets, this is usually a smaller pathway than direct storage of dietary fat, but it becomes more active when carbohydrate intake and total energy intake are high enough. The important point is that the body has several storage layers. A recent meal supplies immediate fuel. Glycogen gives the body a short-term reserve. Triglycerides give the body a longer-term reserve that can last much longer than the sugar stored in liver and muscle. This storage system is older than grocery stores, refrigerators, electric lights, and regular meal schedules. For most of human history, food access changed with season, weather, travel, illness, hunting, gathering, farming, and chance. A body that could save extra energy after a successful meal had a real advantage when the next meal was delayed. So storage belongs to normal metabolism. It is part of how the body protects the brain, warms the body, powers movement, and keeps tissues alive when food is not arriving. A body that stores energy also needs a way to open that storage again. Inside fat cells, triglycerides can wait quietly for hours, days, months, or years. When the signal changes, those stored molecules have to be split apart before their energy can be used. A fat cell does not pour out its stored energy all at once. The triglyceride inside it is held in a large oily droplet, protected inside the cell, waiting for chemical instructions. When the body has plenty of incoming fuel after a meal, insulin is usually higher, and fat storage is easier. When incoming fuel begins to fade, insulin often falls, and stored energy becomes easier to reach. This shift can happen between meals, during a long overnight fast, during exercise, or during any stretch when the body needs more fuel than the bloodstream is currently receiving from food. The stored triglyceride has to be split before it can leave the fat cell. That splitting process is called lipolysis. The word comes from roots that mean fat breaking. Inside the adipocyte, enzymes act like small cutting tools. One important enzyme is hormone-sensitive lipase. Related enzymes also help with the work, including adipose triglyceride lipase, which helps begin the first cut. Together, these enzymes separate a triglyceride into smaller pieces. A triglyceride has one glycerol backbone, with 3 fatty acids attached. During lipolysis, those fatty acids are released one by one. The result is a set of free fatty acids and glycerol. These pieces can move out of the fat cell and enter nearby blood vessels. This is the first real step in taking stored fat out of storage. Hormones help control the timing. Lower insulin generally makes lipolysis easier. Glucagon can support fuel release, especially through its effects on the liver. Adrenaline and noradrenaline, the same signal chemicals involved in stress, cold, and exercise, can also encourage fat cells to release fatty acids. A person walking briskly on a cool morning, climbing a hill, or waking after a long night without food may have more reason to draw on stored fuel. The body does not need panic for this to happen. A quiet overnight fast is enough to shift the balance. Once fatty acids leave a fat cell, they cannot simply drift through watery blood by themselves. Fat and water do not mix well. The bloodstream is mostly water, so fatty acids need a carrier. Many of them travel attached to albumin, a common transport protein made by the liver. Albumin is one of the most abundant proteins in blood plasma. It can carry fatty acids through circulation toward tissues that may use them, such as skeletal muscle, heart muscle, and the liver. Glycerol takes a different path. Because glycerol is more water-friendly than fatty acids, it can travel in the blood more easily. Much of it goes to the liver. There, liver cells can use glycerol as one ingredient for making glucose through gluconeogenesis. That long word means making new glucose from materials that are not carbohydrates. During fasting, this helps the body keep some glucose available for tissues that still need it. Fat release is easy to picture as the same thing as fat burning, but the body handles those steps separately. Lipolysis releases fatty acids from storage. Oxidation is the later process of using those fatty acids for energy inside cells. A fatty acid may leave a fat cell and be carried through the blood, then enter a muscle cell and be burned for energy. A different fatty acid may reach the liver and be changed into another fuel. Some fatty acids can even be restored into triglycerides again, if the body does not need them at that moment. This is one reason metabolism feels more complex than a simple fuel gauge. The body can open storage without using every released molecule right away. It can move fuel from one place to another. It can save some, burn some, and redirect some based on the signals present at that hour. Timing matters. Hormones matter. The needs of different tissues matter. The same stored fat molecule could remain quietly inside an adipocyte during one part of the day, leave during another, and only become useful energy if a cell takes it in and processes it. That is why the phrase burning fat hides several steps inside one familiar idea. Stored fat must be unlocked. Its pieces must travel. A tissue must accept them. Then the cell must move those fatty acids into the machinery that can turn their chemical bonds into usable energy. A fatty acid can enter a working cell through the cell membrane, the thin living boundary that separates the cell from the fluid around it. Skeletal muscle cells, heart muscle cells, and liver cells are especially important places for this to happen. Inside the cell, the fatty acid is prepared for a longer chemical journey. It has to be moved toward mitochondria, the small structures that help turn fuel into ATP. A human cell may have a few hundred mitochondria, while very active cells can have thousands. Heart muscle cells are especially rich in them because the heart needs a steady energy supply from before birth until the final moments of life. Under a microscope, a mitochondrion looks a little like a tiny bean with folded inner walls. Those folds are called cristae. They increase the inner surface area, giving the mitochondrion more room for the chemistry of energy transfer. The fatty acid first goes through a process called beta oxidation. Beta oxidation means the fatty acid chain is clipped apart in small repeating steps. Most fatty acids are long chains of carbon atoms. Palmitic acid, one common fatty acid in the human body and in many foods, has 16 carbon atoms. During beta oxidation, that chain is shortened 2 carbon atoms at a time. Each 2-carbon piece becomes a molecule called acetyl coenzyme A. That name is often shortened to acetyl-CoA. Acetyl-CoA is a central crossing point in metabolism. Fat can lead there. Carbohydrate can lead there. Some amino acids from protein can lead there too. Once acetyl-CoA is made, it can enter the citric acid cycle. This cycle is also called the Krebs cycle, after Hans Krebs, the German-born biochemist who described it in the 1930s. The cycle takes place inside mitochondria. It does not work like a spinning wheel that creates energy by motion. It works as a sequence of enzyme-guided reactions. An enzyme is a protein that helps a chemical reaction happen at the right speed. In the citric acid cycle, carbon atoms from acetyl-CoA are gradually processed. Some leave as carbon dioxide. Other reactions load energy-carrying molecules with high-energy electrons. Those loaded carriers then deliver their electrons to the electron transport chain. The electron transport chain sits along the inner membrane of the mitochondrion. Its name sounds mechanical, and in a way, the image fits. Electrons pass through a series of protein complexes, step by step. As they move, the mitochondrion uses their energy to pump hydrogen ions across the inner membrane. This creates a difference between the two sides of the membrane, almost like water held behind a tiny dam. The hydrogen ions then flow back through a protein machine called ATP synthase. As they pass through it, ATP synthase helps build ATP from smaller parts. This is one of the body's most important energy-making steps. Oxygen becomes essential near the end. It accepts electrons after they have moved through the chain. When oxygen accepts electrons and combines with hydrogen, water is formed. This is one reason breathing and metabolism are tied together so closely. The oxygen drawn into the lungs is carried by hemoglobin inside red blood cells. It travels through arteries, capillaries, and into tissues, where cells can use it inside mitochondria. Carbon dioxide moves the opposite way. It is made during fuel oxidation, carried back through the blood, delivered to the lungs, and breathed out. Every quiet breath is connected to the chemistry of stored fuel. A long exhale carries away carbon atoms that may have once been part of bread, olive oil, rice, salmon, butter, or body fat. Heat is released along the way because energy transfer is never perfectly efficient. Some energy becomes ATP. Some spreads as warmth. That warmth helps maintain body temperature near 37 degrees Celsius, even in a still room, under blankets, during sleep. So the familiar phrase burning fat points to many linked steps. A fatty acid is released from storage. A carrier moves it through blood. A cell takes it in. Mitochondria shorten it, process it, pass electrons, use oxygen, make ATP, release carbon dioxide, produce water, and give off heat. This hidden work is happening across tissues all the time. Some tissues ask for far more energy than others, even when the body appears completely still. The largest quiet demand often comes from organs that make up only a small part of body weight. A resting adult body may look still from the outside, but inside the chest, skull, and abdomen, several organs are spending energy every second. The brain, liver, heart, and kidneys together can account for roughly 60 to 70% of resting energy use in many adults. Together, they usually make up less than 6% of total body weight. That difference is one of the most important clues in metabolism. A kilogram of tissue does not always cost the same amount of energy to maintain. Heart tissue and kidney tissue use far more energy per kilogram than skeletal muscle or fat tissue. The heart is built for constant contraction. It squeezes blood through the body more than 100,000 times in a day. Each beat needs careful movement of calcium, sodium, and potassium ions across heart cell membranes. An ion is a charged particle, and cells use these charged particles to create electrical signals and muscle movement. The heart cannot pause for repairs the way a tired leg muscle can rest after a long walk. It has to keep working during sleep, illness, fasting, and deep stillness. The brain has a different kind of demand. It is soft tissue, only about 2% of adult body weight, but it often uses around 1/5 of the body's resting energy. Much of that energy goes toward maintaining electrical readiness. Brain cells keep sodium and potassium on different sides of their membranes. That separation works like a tiny battery. When a nerve signal travels, charged particles rush through small channels, and then the cell spends energy restoring the balance. A thought, a dream, a remembered sound, and the quiet control of breathing all depend on this hidden electrical work. The liver sits under the right side of the rib cage and weighs roughly 1.5 kilograms in many adults. It is one of the body's great chemical sorting centers. After nutrients arrive from the intestines through the portal vein, liver cells help decide what to store, release, transform, or break down. The liver stores glycogen, releases glucose between meals, makes bile for fat digestion, builds blood proteins such as albumin, processes alcohol and medications, and converts ammonia from protein breakdown into urea so the kidneys can remove it. These jobs take energy because the liver is constantly changing molecules from one form into another. The kidneys are smaller, each shaped a little like a bean, and each one is usually about the size of a fist. They sit toward the back of the abdomen on either side of the spine. Every day, blood passes through tiny filtering units called nephrons. Each kidney contains about 1 million nephrons. They filter fluid, reclaim useful substances, remove wastes, and adjust the balance of sodium, potassium, water, acids, and bicarbonate. That sorting work depends on pumps in kidney cells. A pump is a protein that uses energy to move substances across a membrane, often against the direction they would naturally flow. This is why kidney tissue has such a high resting energy cost. Skeletal muscle tells a slightly different story. Because the body contains so much muscle, it contributes a meaningful share of resting energy use. A person with more muscle generally has more tissue to maintain. Muscle cells need energy for repair, protein turnover, ion balance, and readiness for movement. Still, per kilogram, resting muscle spends much less energy than the heart, liver, brain, or kidneys. Fat tissue spends less energy per kilogram than muscle, but it remains alive and active. Fat cells need blood flow. They respond to insulin. They release fatty acids. They produce chemical signals, including leptin, which helps inform the brain about stored energy. So body fat is not metabolically silent, even when its resting energy cost is lower than that of many lean tissues. This is where the phrase fast or slow metabolism becomes more specific. A body is not a single object burning fuel at one simple speed. It is a collection of tissues with different costs. Two bodies can have different resting energy needs because their organs, muscles, fat tissue, blood volume, and total size are arranged differently. Some of that difference can be seen from the outside. Much of it is hidden in the organs that keep working through the night. Once tissue type matters, body size and body composition become part of the story, because the body has to spend energy maintaining every living part it carries. A body with more living tissue usually has more daily maintenance work to do. More cells have to keep their membranes balanced. More blood has to be moved through vessels. More tissue has to be warmed, repaired, supplied with oxygen, and cleared of waste. This is why a larger adult body will usually burn more total energy across a day than a smaller adult body, even when both people are resting for many hours. The useful phrase here is total daily energy expenditure. It means all the energy a body uses in one day. Resting metabolic rate is one part of that total. Daily movement is another part. Digesting food adds a smaller part. Exercise can add more, depending on the activity, the person's size, the time spent moving, and the effort involved. When people talk about a fast or slow metabolism, they often mean the whole day. A body's total energy use, though, is built from several layers. The resting layer is especially important because it continues through the entire day and night. A sleeping person still has a brain using glucose and oxygen. A liver still has chemical work to do. The heart still pushes blood through roughly 60,000 miles of blood vessels. If every vessel in the body were placed end to end. Kidneys still filter blood through tiny nephrons. Skin cells still divide and repair. Bone marrow still makes new blood cells. A larger body tends to have more of these tissues, and that changes the total energy cost. Body composition matters too. One of the strongest predictors of resting metabolic rate is fat-free mass. Fat-free mass means the body's weight after fat tissue is set aside. It includes organs, skeletal muscle, bone, blood, connective tissue, and much of the body's water-rich tissue. This does not mean all lean tissue burns energy at the same rate. The brain, liver, heart, and kidneys are very expensive tissues to maintain. Skeletal muscle is less expensive per kilogram than those organs, but the body can carry much more muscle than liver or heart tissue. That makes muscle important because of its total amount. Fat tissue also uses energy. An adipocyte has to stay alive, respond to insulin, store triglycerides, release fatty acids, and send chemical signals. Fat tissue has blood vessels, nerves, immune cells, and connective tissue around it. Even so, fat tissue has a lower resting energy demand per kilogram than many lean tissues. This difference helps explain why two bodies of the same weight can have different energy needs. Imagine two adults who both weigh the same amount. One may be taller with longer limbs, more blood volume, and more total lean tissue. The other may have a different mix of fat tissue, muscle, and organ size. Their scale weight could match, while their resting energy use differs. Height matters as well. A taller body often has more surface area, more tissue volume, longer bones, and more blood to circulate. Organ size can differ quietly between people. Muscle mass can differ from years of work, sport, illness, aging, injury, or ordinary daily habits. These differences do not make one body better than another. They simply change the amount of living material the metabolism has to maintain. A person with more total tissue usually needs more energy to keep that tissue alive. A person with more fat-free mass often has a higher resting energy use than someone with less fat-free mass. The effect of muscle should stay in proportion. Muscle helps shape resting metabolism, movement, strength, glucose storage, and daily function. It does not act like a giant hidden furnace that melts fat on its own. A pound of added muscle changes the body's daily energy needs only modestly. Its larger importance comes from how it supports movement, posture, balance, blood sugar handling, and physical independence over time. The same careful thinking applies to body fat. Stored fat carries energy, but it also adds tissue that must be supplied and regulated. As fat mass rises, total energy use often rises too, because the body is larger. At the same time, energy use relative to body weight may look different, because fat tissue spends less energy per unit than many lean tissues. This is why total burn and relative burn can tell different stories. A bigger body may burn more total energy in a day. A smaller body may burn less total energy. while using more energy for each kilogram of its weight. Metabolism depends on size, tissue type, and the hidden costs of maintenance. Those pieces explain a great deal. Still, even two bodies with similar height, weight, and body composition can use energy differently, because some of metabolism is shaped by signals that are harder to see. A person's visible build can explain a large part of daily energy use, yet it leaves some quiet differences unaccounted for. Two adults may stand at the same height, carry similar weight, have similar muscle mass, and still show different resting metabolic rates when measured carefully. Part of that difference can come from organ size. The liver, heart, kidneys, and brain do so much chemical and electrical work that small differences in their size can change the body's resting energy demand. A slightly larger liver may process more blood, store more glycogen, make more proteins, and handle more chemical conversions each day. Kidney tissue is also expensive to run because it uses energy to move sodium, potassium, acids, and water across tiny filtering structures. These details are hidden beneath the skin, so two bodies can look alike while carrying different internal energy costs. Hormones add another layer. The thyroid gland sits low in the front of the neck, wrapped partly around the windpipe. It makes thyroid hormones, mainly thyroxine and triiodothyronine, often shortened in medical language to T4 and T3. These hormones help set the pace of energy use in many tissues. They influence how cells make proteins, use oxygen, handle heat, and respond to other signals. When thyroid hormone activity is higher, many cells tend to spend more energy. When thyroid hormone activity is lower, many processes can slow down. This does not mean small day-to-day changes in weight are always caused by the thyroid. It means the thyroid is one of the body's broad regulators, like a central volume control affecting many instruments at once. The nervous system also shapes metabolism in quieter ways. One branch is called the sympathetic nervous system. It helps prepare the body for alertness, cold, movement, and stress. Its signals can raise heart rate, tighten or relax blood vessels in different areas, increase heat production, and encourage stored fuel to move into circulation. Adrenaline and noradrenaline are two important signal chemicals in this system. During a brisk walk, a cold morning, or a sudden startle, these signals can help make more fuel available. They can also affect fat cells by encouraging the release of fatty acids when the body may need extra energy. Even at rest, people can differ in nervous system tone. One person may naturally run with a slightly higher heart rate, warmer hands, more restlessness, or more heat production. Another person may sit more still, cool down more easily, or conserve energy more strongly. These differences can be small in 1 hour and meaningful across many months. Inherited biology also matters. Genes help build the receptors, enzymes, hormones, and brain circuits that guide appetite, storage, body size, and fuel use. There is no single common metabolism gene that explains ordinary body differences. The more accurate picture is a web of many genes, each adding a small effect, mixed with sleep, diet, age, illness, medication, stress, and daily environment. A few rare genetic pathways show how powerful these systems can be. Leptin is a hormone made mostly by fat cells, and it helps signal stored energy to the brain. The melanocortin-4 receptor is part of a brain pathway involved in appetite and energy balance. Rare changes in this receptor can strongly affect hunger and body weight. These examples are useful because they show that the brain is deeply involved in body weight regulation. They should be treated as specific cases, rather than common explanations for everyone who gains or loses weight differently. Cellular efficiency adds another quiet difference. Some cells may waste a little more energy as heat. Others may capture more energy into ATP. Mitochondria can vary in number and function between tissues and people. Training, aging, illness, nutrition, and genetics can all influence those tiny energy systems over time. A body is constantly adjusting, and those adjustments do not always show up clearly in the mirror. This is why metabolism can feel unfair from the outside. People compare meals, workouts, or body shapes, while many of the important controls are hidden in organ size, hormone signaling, nerve activity, inherited pathways, and cellular chemistry. The body's energy use is layered. Some layers are structural, some are chemical, some are electrical. A few layers are almost invisible because they appear as ordinary habits. A person may tap a foot, stand more often, shift in a chair, pace during phone calls, or walk from room to room without thinking of it as exercise. Those small movements can become one of the largest quiet differences in daily energy use. A foot tapping under a desk can look too small to matter. A person shifting in a chair, standing during a phone call, walking to the kitchen, folding laundry, carrying groceries, or pacing near a window may seem far away from the idea of metabolism. Yet the body counts all movement. It counts the movement that happens in a gym. It also counts the movement that happens between ordinary moments. Scientists call this non-exercise activity thermogenesis, often shortened to NEAT. Thermogenesis means heat making. In plain language, NEAT is the energy spent on daily movement that is outside sleeping, eating, and planned exercise. It includes posture. It includes standing. It includes walking from room to room, reaching for a shelf, cleaning a counter, brushing teeth, changing clothes, cooking dinner, taking stairs, and carrying a backpack. Small motions can be hard to notice because they are spread thinly across the day. A few steps across a room may not mean much by itself. A few hundred small movements, repeated from morning to night, can change the total amount of energy the body uses. This is one reason two people with similar bodies can have different daily energy needs. One person may sit very still while reading, working, or watching a screen. Another person may shift position often, stretch a leg, tap a hand, stand up without thinking, or walk around during short breaks. Neither person may describe that as exercise. Their muscles, however, are still using ATP. Their hearts still move more blood. Their breathing may rise slightly. Their body heat changes in tiny amounts. Across many waking hours, those small costs can accumulate. A classic overfeeding study in the late 1990s showed how different this response can be. 16 adults were given about 1,000 extra calories each day for 8 weeks. They were not all forced into the same movement pattern. Some people stored much more of the extra energy as fat. Others increased ordinary daily movement enough to burn a large share of the extra energy. The difference was not explained by formal workouts. It came largely from changes in NEAT, the quiet energy spent through ordinary movement. That study became important because it showed how differently bodies can respond when more food arrives. One body may become more restless without much awareness. Another may conserve more of the extra energy. Fidgeting has been measured in smaller ways too. A person sitting still in a chair uses less energy than a person sitting while shifting, tapping, moving the legs, or changing posture. The difference during a single minute can seem modest. Over a school day, a work day, or a long evening at home, the difference becomes more meaningful. Modern life can reduce this hidden movement without anyone making a clear decision. Cars reduce walking. Elevators replace stairs. Remote work can remove a commute. Food delivery reduces errands. Streaming, phones, and long computer sessions can keep the body in one position for hours. A person living in a city with sidewalks, transit stops, stairs, shops, and errands close by may gather many small movements without planning them. A person in a car-focused suburb may need deliberate effort to get the same background motion. Work also matters. A nurse, server, warehouse worker, cleaner, teacher, or parent of a toddler may spend hours standing, turning, lifting, and walking. A student, editor, driver, programmer, or office worker may spend much of the day seated. Those differences change energy use before anyone thinks about exercise. Biology shapes this too. Sleep loss can make a body feel heavier and less willing to move. Stress may make one person pace and another person freeze into stillness. Pain can reduce small movements all day. Mood, habit, medication, temperature, and job demands can all change how often a body chooses motion. Even hunger and fullness can affect restlessness, because the brain is always reading fuel signals and adjusting behavior. So ordinary movement belongs inside metabolism. It is not a moral score. It is one of the ways a body spends energy in real life. The hidden burn of daily movement sits between biology and environment, shaped by rooms, jobs, sleep, stress, appetite, joints, muscles, and nervous system signals. Those signals lead back toward fat itself, because stored energy is not silent inside the body. Fat tissue sends chemical messages that can influence hunger, storage, release, and the urge to move. Those messages begin inside adipose tissue, the soft storage tissue found under the skin and around deeper organs. Adipose tissue stores triglycerides, but it also listens and responds. Blood vessels bring it oxygen, glucose, fatty acids, insulin, and stress hormones. Nerve endings reach into it. Immune cells move through it. A fat cell is part of a living communication network. Scientists call adipose tissue an endocrine tissue. Endocrine means it releases chemical signals into the blood. The thyroid gland, pancreas, ovaries, testes, and adrenal glands are better known endocrine organs. Fat tissue belongs in that same broad category because it sends hormones and signaling proteins that other tissues can read. One of its best-known signals is leptin. Leptin was identified in the 1990s, and its discovery changed how scientists thought about body fat. The word comes from the Greek word leptos, meaning thin. Fat cells make leptin, and in general, more stored fat means more leptin moving through the blood. Leptin travels to the brain, including a small region called the hypothalamus. The hypothalamus sits deep near the base of the brain. It helps regulate hunger, thirst, body temperature, sleep timing, stress hormones, and reproductive hormones. It is small, about the size of an almond, but it helps coordinate many basic survival signals. Leptin gives the hypothalamus information about stored energy. When stored energy is low, leptin usually falls. That can make hunger stronger and energy conservation more likely. When stored energy is higher, leptin usually rises. In a simple picture, that should tell the brain that energy is available. The real body adds more context. Leptin does not work like a single fullness switch. Some people have high leptin levels because they have more fat tissue, while the brain may respond less strongly to that signal. This reduced response is often called leptin resistance. The signal exists, but the message is not received with full strength. Inflammation, long-term high energy stores, sleep patterns, genetics, and other signals may all influence how leptin is handled. Leptin also works alongside many other messengers. Insulin, made by beta cells in the pancreas, rises after many meals and helps move glucose into cells. It also carries information about fuel availability. Ghrelin comes mainly from the stomach. It often rises before meals, when the stomach has been empty for a while. People sometimes call it a hunger hormone, though it also affects digestion, growth hormone release, and reward pathways connected to food. After food reaches the intestine, other hormones join the conversation. GLP-1 is released from cells in the gut after eating. It helps support insulin release when glucose is present, slows stomach emptying, and contributes to fullness. Peptide YY is also released from the gut, especially after meals, and helps reduce appetite for a time. These signals do not float around as isolated facts. They arrive together, shaped by the meal, the time of day, sleep, stress, past weight change, body fat, movement, and the nervous system. A breakfast with protein, fiber, and fat may create a different signal pattern than a sweet drink that leaves the stomach quickly. A night of poor sleep can shift hunger and fullness signals the following day. A long period of dieting can lower leptin and increase hunger even after the person has eaten. This is why appetite and energy use are linked. The brain is not simply asking how much food is in the stomach. It is also reading stored energy, recent fuel, blood glucose, gut stretch, hormone patterns, body temperature, stress state, and expected energy needs. Fat tissue sits inside that larger conversation. It stores energy when signals favor storage. It releases fatty acids when signals favor fuel use. It sends leptin and other chemical messages. It responds to insulin, adrenaline, noradrenaline, immune signals, and nutrients in the blood. Body fat, then, is active information-bearing tissue. Its signals can influence hunger, storage, release, movement, and the amount of energy the body is willing to spend. Those signals become especially important when food stops arriving for a while. As the bloodstream receives less incoming fuel, the body begins shifting from the fed state into stored fuel, and metabolism changes its pattern hour by hour. Several hours after a meal, the body begins to leave the fed state. The stomach empties more slowly if the meal contained fat, protein, or fiber. The small intestine may keep absorbing nutrients for a while, especially after a larger mixed meal. Gradually, though, the stream of new glucose, amino acids, and fats becomes thinner. As less glucose enters the blood from the intestine, insulin usually falls. That change matters because insulin strongly shapes the body's storage mode. When insulin is higher, cells are encouraged to take in glucose, build glycogen, and store extra fuel. When insulin falls, stored fuel becomes easier to reach. Another pancreatic hormone, called glucagon, becomes more important during this shift. Glucagon is made by alpha cells in the pancreas. It helps the liver keep blood glucose within a usable range when food is no longer arriving. The liver's first reserve is glycogen. Glycogen is stored carbohydrate, built from many glucose units linked together. During an overnight fast, liver cells can break glycogen apart and release glucose into the blood. This helps supply tissues that rely heavily on glucose, including red blood cells and parts of the brain. Muscle has glycogen too, sometimes a large amount depending on muscle size, training, and recent meals. Muscle glycogen mostly stays in the muscle that stores it. A muscle cell lacks the main enzyme needed to release free glucose into the bloodstream. So the glycogen in a thigh muscle can help power walking or climbing stairs, while liver glycogen helps steady blood glucose for the whole body. As the hours without food continue, fat release becomes more active. Lower insulin makes lipolysis easier. Adrenaline and noradrenaline can also support fat release, especially during movement, cold, or longer gaps between meals. Inside adipocytes, stored triglycerides are split into fatty acids and glycerol. Fatty acids travel through the blood attached to albumin. Muscle, liver, and heart tissue can take in those fatty acids and use them for energy. The heart is especially comfortable using fatty acids during ordinary resting conditions. It needs constant fuel because it beats without long pauses, day and night. The glycerol piece has a different use. It can travel to the liver and become one material for gluconeogenesis. Gluconeogenesis means making new glucose from sources that are not carbohydrates. Glycerol can contribute. Certain amino acids can contribute too. Lactate, which is made by working cells and red blood cells, can also return to the liver and be changed back toward glucose. This process helps protect blood glucose when liver glycogen begins to run lower. The body's fuel use changes gradually during fasting. There is overlap. Some glucose is still being used. Some fatty acids are being released and burned. Some liver glycogen may still remain. Some new glucose may be made. As fasting lasts longer, the liver can also make ketone bodies. Ketone bodies are small water-soluble fuels made from fat-derived molecules. The main ones are acetoacetate and beta-hydroxybutyrate. The liver releases them into the blood, and other tissues can use them for energy. During longer fasting or very low carbohydrate intake, the brain can use ketones as a partial fuel. It still needs some glucose, but ketones can reduce how much glucose has to be made from other materials. This is one of the body's important survival adaptations. It helps spare some protein-containing tissue during periods when food is scarce. Fasting shows metabolic flexibility clearly. A body can move from recent food to liver glycogen. It can draw more from stored fat. It can make some glucose when needed. It can produce ketones when the conditions last long enough. The pattern depends on meal size, activity, body composition, sleep, liver glycogen, hormones, and the length of time without food. A short overnight fast and a long multi-day fast do not create the same internal landscape. The body is always matching fuel use to the situation. That flexibility is one reason humans can sleep through the night without eating every hour. It is also one reason stored fat matters so much. Stored energy gives the body time. It gives the brain, heart, muscles, liver, and kidneys a way to keep working when food is delayed. When low energy continues for longer, the body begins doing more than switching fuels. It starts protecting energy, lowering costs, and adjusting its signals around scarcity. Over days and weeks, a shortage of energy becomes more than a fuel problem. It becomes information. The body begins reading the pattern as scarcity, and many systems adjust at once. The first change is simple. A smaller body usually costs less energy to maintain. Less tissue means fewer cells to supply with oxygen. A lighter body takes less energy to move across a room. A smaller liver, smaller muscles, and reduced total body mass all lower daily energy needs. So when a person loses weight, resting energy use often falls for ordinary physical reasons. There is less living material to keep warm, repair, and circulate blood through. Then a second layer can appear. Energy expenditure may fall more than body size alone would predict. This is called adaptive thermogenesis. Thermogenesis means heat making, and adaptive means the body is adjusting to conditions. In plain language, adaptive thermogenesis is a conservation response. The body spends less energy than expected because it has sensed a longer period of limited fuel. Several signals can shift during this state. Leptin often falls as fat stores shrink. Insulin may fall as less fuel arrives and less stored energy is available. Thyroid hormone activity can change, which affects how quickly many cells use energy. The sympathetic nervous system may become less active in some ways, reducing signals tied to heat production, alertness, and fuel release. Heart rate can slow. Body temperature may run slightly lower. Small, spontaneous movements may fade before the person notices them. A person may sit more still, move less often, feel colder, or become more focused on food. These changes are not imaginary. They are part of a coordinated energy-saving pattern. One of the most famous examples came from the University of Minnesota during the 1940s. The study is often called the Minnesota Starvation Experiment. It was led by physiologist Ancel Keys and involved adult male volunteers, many of them conscientious objectors during the Second World War. The men were studied through a controlled period of normal eating, then a long period of semi-starvation, followed by recovery. During the semi-starvation phase, their food intake was sharply reduced for months. Researchers measured body weight, strength, heart rate, temperature, mood, hunger, and many physical changes. The published report, called The Biology of Human Starvation, came out in 1950. It became an important historical record of how the human body responds when energy shortage continues. The study should be handled with care. It was extreme compared with ordinary modern dieting, and it took place in a very specific wartime context. Its value here is not as an example to follow. Its value is that it made the body's conservation response visible. As the men lost weight, they became colder, weaker, slower, and more preoccupied with food. Their resting metabolism dropped. Their heart rates fell. Their bodies became better at spending less. Modern studies of weight loss and caloric restriction show related patterns, though the size and duration of the response can vary. Some people show a larger adaptation. Some show a smaller one. Sleep, stress, protein intake, physical activity, hormones, starting body size, genetics, and the length of restriction can all affect the response. This makes metabolism difficult to describe with one rule. A drop in energy expenditure after weight loss can come from the body being smaller. It can also come from the body becoming more conservative. Both pieces can exist together. The same idea helps explain why long-term changes in body weight can feel different from simple math. A body that has lost stored energy may send stronger hunger signals. It may reduce background movement. It may lower some energy costs. It may become more efficient during familiar tasks. These adjustments can protect the body during true food shortage. In modern life, they can also make weight change feel frustrating and uneven. The deeper point is that stored energy has meaning to the body. Fat is not only weight on a scale. It is fuel reserve, hormone source, insulation, and part of the body's survival map. To understand why the body defends it, fat tissue has to be seen more closely, as living tissue with blood vessels, signals, structure, and work of its own. Under the skin and around deeper organs, adipose tissue forms a living network. It has blood supply. It has nerves. It has immune cells. It has connective fibers that help hold its shape. The main kind of long-term storage fat in adults is called white adipose tissue. This is the soft, pale fat most people picture when they think of body fat. Its main storage cells are adipocytes. Each adipocyte can hold a droplet of triglyceride, the same stored fat molecule made from 3 fatty acids attached to glycerol. When an adipocyte stores more triglyceride, it can grow larger. Some fat cells can become many times bigger than their earlier size. If storage demand continues for a long time, the body can also make new fat cells from precursor cells, which are earlier cells that can develop into mature adipocytes. This gives fat tissue 2 ways to expand. Existing cells can grow. New cells can be added. That growth requires support. A fat cell cannot live as an isolated bubble. It needs oxygen from nearby blood vessels. It needs nutrients. It needs a way to release fatty acids when the body calls for stored fuel. It needs signals from insulin, adrenaline, noradrenaline. thyroid-related systems, immune cells, and the nervous system. Adipose tissue also sends messages back. It produces leptin, the hormone that helps inform the brain about stored energy. It also produces adiponectin, a signaling protein linked to how tissues handle fats and respond to insulin. Higher adiponectin is often connected with better insulin sensitivity, which means cells respond more effectively to insulin's message. These signals help explain why fat tissue behaves like an organ-like system. An organ is usually thought of as a body part with a specific job, such as the liver, heart, or kidney. Adipose tissue has several jobs at once. It stores long-term fuel. It cushions parts of the body. It helps insulate against cold. It releases fatty acids between meals or during longer energy demand. It also communicates with the brain, liver, muscles, blood vessels, and immune system. Location changes its behavior. Subcutaneous fat lies under the skin. It is the fat someone can usually pinch at the belly, thigh, hip, arm, or back. This layer helps shape the body, soften impact, and reduce heat loss. In cold weather, subcutaneous fat can slow the movement of heat from warm inner tissue toward the outside air. Visceral fat sits deeper in the abdomen, around organs such as the intestines and liver. It cannot be seen directly from the outside. Two people can have similar waist size and still carry different amounts of deeper abdominal fat. Visceral fat drains into blood vessels that lead toward the liver, which gives it a close chemical connection to liver metabolism. It is also often more active in inflammatory signaling. Inflammation is the immune system's way of responding to stress, injury, infection, or irritation. A small amount of immune activity helps tissue repair and defense. Long-lasting inflammatory signaling inside fat tissue can affect how nearby cells respond to insulin and other signals. This does not make visceral fat something to fear in a dramatic way. It means fat location matters. Subcutaneous and visceral fat differ in blood flow, hormone response, immune activity, and how strongly they are linked with metabolic risk. The body also stores small amounts of fat in other places. Fat can be found around the kidneys as padding. Bone marrow contains fat cells. Muscles can store tiny droplets of fat that trained endurance athletes may use as local fuel. The skin has a fatty layer that helps with shape and insulation. These different depots show that body fat is arranged, supplied, and regulated. It is built into the body's structure. Fat tissue can also become strained. As adipocytes grow, the tissue may need more blood vessels to keep up. If oxygen supply becomes limited in crowded areas of fat tissue, stress signals can rise. Immune cells may gather. The tissue can become less flexible in how it stores and releases fuel. This is one reason body fat biology depends on storage capacity, blood flow, location, and hormone response, rather than scale weight alone. Stored fat has helped humans survive seasons of hunger, long winters, illness, pregnancy, childhood growth, travel, and heavy physical work. It remains part of ordinary metabolism. Its behavior can be helpful, inconvenient, protective, or risky depending on amount, location, and context. White fat is the main storage tissue, but adipose tissue has another form with a very different purpose. Some fat cells are packed with mitochondria and built to spend fuel as heat. Brown fat sits in a different part of the adipose story. Its full name is brown adipose tissue, and its main job is heat production. The color comes from two features packed into the tissue. Brown fat has many tiny blood vessels, which bring oxygen and carry warmth away. It also has many mitochondria, the same small cell structures that help process fuel. Those mitochondria contain iron-rich proteins, and together with the blood supply, they give the tissue a darker reddish-brown appearance. White fat often holds one large oil glomerule droplet inside each cell. Brown fat cells tend to contain many smaller fat droplets instead. That arrangement gives the cell quick access to fuel. A brown fat cell is built for rapid use, especially when the body needs warmth. The key mechanism is a protein called UCP1. Its full name is uncoupling protein 1. Normally, mitochondria use fuel to help build ATP, the small energy packet cells use for work. Inside a mitochondrion, hydrogen ions collect on one side of the inner membrane, creating a tiny stored force. Those ions usually flow back through ATP synthase, the protein machine that helps make ATP. UCP1 gives some of those hydrogen ions another path. When UCP1 is active, the mitochondrion releases more of the fuel's energy as heat. The cell is still using fuel. The body is still consuming oxygen. Energy is being spent in a controlled way, with warmth as the main result. This is called non-shivering thermogenesis. Thermogenesis means heat making. Non-shivering means the heat is produced without the rapid muscle shaking that happens when someone shivers in the cold. This matters especially in newborn babies. A newborn has a large head, a small body, thin muscles, and a high surface area compared with body size. That means heat can leave the body quickly. Babies also cannot shiver as effectively as adults. Brown fat helps protect them by making heat directly. Important deposits in babies are found around the neck, shoulders, spine, and upper back. For a long time, adult humans were thought to have very little useful brown fat. Modern imaging changed that view. Scans that track active glucose use have shown that many adults can still have brown fat deposits, especially around the neck, collarbone, upper chest, and along parts of the spine. These areas often become more active in cool conditions. Cold exposure can activate the sympathetic nervous system, the branch involved in alertness, fuel release, and temperature defense. Nerve signals then reach brown fat and release noradrenaline. That signal encourages brown fat cells to draw in fuel and turn on heat production. The fuel can include fatty acids stored inside brown fat cells. It can also include glucose and fatty acids arriving from the blood. This connects brown fat to the wider metabolism story. A body in a cool room may quietly spend more energy to defend its temperature. Hands may feel colder. Blood vessels near the skin may narrow. Muscles may eventually shiver. Brown fat can add a deeper layer of heat production before or alongside those visible responses. Researchers also study beige fat. Beige fat refers to fat cells within white fat depots that can take on some brown fat-like features. Under certain conditions, such as repeated cold exposure, some white fat areas may develop cells with more mitochondria and more heat-making ability. This process is sometimes called browning. The effect varies by person, age, body composition, temperature exposure, and biology. Brown fat has drawn attention because it spends energy rather than storing it. That makes it tempting to imagine it as a simple answer to body weight. The real picture is more measured. Brown fat activity can contribute to heat production and energy use. It may play a role in glucose handling, cold adaptation, and metabolic health. Its effect in adults differs from person to person, and it does not erase the larger roles of food intake, movement, sleep, hormones, muscle, liver function, and total body size. Still, brown fat changes the meaning of fat itself. Adipose tissue can store fuel for months. It can send hormone signals to the brain. In this darker form, it can also spend fuel to warm the body. Heat, then, is part of metabolism from several directions. Cold can call heat out of brown fat. Movement can release heat from muscle. Even a meal brings a smaller rise in energy use because digestion and nutrient processing have their own quiet cost. After a meal, body heat can rise slightly for a simple reason. Digestion has a cost. The stomach has to churn. The pancreas has to release enzymes. The gallbladder may squeeze bile into the small intestine. Cells lining the gut have to move nutrients across membranes, package them, and send them into blood or lymph. The liver then receives much of that incoming material and begins sorting it. This temporary rise in energy use is called the thermic effect of food. Thermic means related to heat. The thermic effect of food is the energy the body spends digesting, absorbing, transporting, and processing nutrients after eating. It is one reason a meal becomes part of metabolism before any of its fuel is stored or burned. Protein usually has the highest processing cost. A rough range often used is that protein may cost about 20 to 30% of its own energy to handle. So if protein brings energy into the body, a noticeable share of that energy is spent just processing it. Carbohydrate usually has a smaller cost, often around 5 to 10%. Fat tends to have the lowest processing cost, often around 0 to 3%. These numbers are not exact for every person or every meal. They shift with meal size, food form, digestion speed, body state, and the mixture of nutrients eaten together. Still, the pattern is useful. The body handles protein, carbohydrate, and fat through different chemical paths. Protein costs more because amino acids require extra sorting. When protein from eggs, fish, lentils, yogurt, chicken, beans, or tofu is digested, it becomes amino acids. Those amino acids can build enzymes, transport proteins, immune proteins, muscle proteins, skin structures, and repair materials. The body also has to remove nitrogen from amino acids when they are used for energy or changed into other molecules. That nitrogen is handled through the liver's urea cycle. Urea is a waste product that can travel through the blood to the kidneys and leave in urine. This extra handling helps explain why protein has a higher thermic effect. Carbohydrate has a different route. Starches from rice, oats, potatoes, bread, corn, or pasta are broken down toward glucose. Glucose can enter the blood, move into cells with the help of insulin, refill glycogen in liver and muscle, or be used to make ATP. When glycogen stores have room, the body can pack glucose away in that short-term form. When energy intake is high enough and conditions favor storage, the liver can change some carbohydrate into fat, though this pathway usually plays a smaller role in ordinary mixed diets than many people imagine. Fat is especially efficient to process and store. Dietary fat from olive oil, butter, nuts, cheese, avocado, salmon, or meat is already chemically close to the triglycerides stored inside adipocytes. After digestion and absorption, many fatty acids are rebuilt into triglycerides inside intestinal cells. They are packed into chylomicrons, travel through lymph, enter the bloodstream, and can later be delivered to tissues. If the body is storing energy, fat cells can take up those fatty acids and place them into triglyceride droplets, with relatively little chemical rebuilding compared with carbohydrate or protein. This efficiency helps explain why fat is such a compact long-term fuel. It carries about 9 calories per gram, compared with about 4 calories per gram for carbohydrate or protein. The body also meets a nutrient that follows a quieter path. Fiber is a kind of carbohydrate found in plant foods such as oats, beans, apples, berries, carrots, lentils, whole grains, and vegetables. Human digestive enzymes cannot fully break many fibers apart in the small intestine. Some fiber holds water and changes the texture of food inside the gut. Some slows digestion. Some passes onward with much of its structure still intact. By the time fiber reaches the large intestine, the meal has entered a different kind of metabolic space. The body's own cells have done much of their work, but they are no longer working alone. In the colon, trillions of microbes can meet the leftovers of digestion and begin their own quiet chemistry. In the colon, digestion becomes shared work. The large intestine is wider and shorter than the small intestine, and it moves material more slowly. Its main sections are the cecum, ascending colon, transverse colon, descending colon, sigmoid colon, and rectum. By the time food remnants arrive there, much of the glucose, amino acids, and dietary fat has already been absorbed. What remains includes water, minerals, mucus, shed intestinal cells, resistant starch, and fibers the human small intestine could only partly handle. Resistant starch is starch that escapes digestion earlier in the gut. It can come from foods such as beans, lentils, oats, green bananas, cooked and cooled potatoes, and cooked and cooled rice. Inside the colon, large communities of microbes meet those leftovers. These microbes include bacteria, viruses, fungi, and other tiny organisms, though bacteria are usually the main focus in metabolism research. Common bacterial groups include bacteroids, firmicutes, bifidobacterium, and lactobacillus. Together, this living community is called the gut microbiome. A microbiome is the collection of tiny organisms living in a particular environment. The colon is warm, moist, low in oxygen, and rich in slow-moving material, which makes it a suitable place for many of these microbes to live. Some gut bacteria can ferment fiber. Fermentation means they break down molecules without using oxygen, in the same way human mitochondria do. The result is a set of small molecules called short-chain fatty acids. 3 important ones are acetate, propionate, and butyrate. Acetate can travel through the blood and be used by different tissues. Propionate goes mainly to the liver, where it can enter pathways connected to glucose and fat metabolism. Butyrate is especially important for the cells lining the colon. Colon cells can use butyrate as a fuel, which helps support the gut lining. That lining matters because the inside of the intestine is full of food fragments, bacteria, bile acids, enzymes, and waste. A healthy gut barrier helps separate the inner world of the colon from the bloodstream. It allows useful molecules to cross in controlled ways, while keeping larger irritants and many microbes in place. Short-chain fatty acids can also influence immune activity inside the gut. Immune cells constantly sample the intestinal environment. They help tolerate helpful microbes, respond to harmful ones, and repair damage when the lining is stressed. This means the microbiome can affect metabolism indirectly through the gut barrier and immune signaling. Bile acids add another layer. The liver makes bile acids from cholesterol. They are released into the small intestine as part of bile, where they help break large fat droplets into smaller droplets. Most bile acids are later absorbed and returned to the liver. Some reach the colon, where bacteria can modify them. These changed bile acids do more than help digestion. They can also act as signals, reaching receptors in the intestine, liver, and other tissues. Through those signals, bile acids can influence glucose handling, fat processing, and energy use in small but meaningful ways. Gut microbes may also affect appetite signals. When fiber is fermented and short-chain fatty acids are produced, cells in the gut lining can respond by releasing hormones linked to fullness and post-meal regulation. These include GLP-1 and peptide YY, the same gut signals connected earlier to appetite and fuel handling. The effect depends on the person, the food, the microbes present, and the rest of the body's state. The microbiome is a real metabolic influence, though it belongs in proportion. A single probiotic capsule does not rewrite the entire energy system. One food does not instantly create a new metabolism. The gut community changes with long-term diet patterns, antibiotics, illness, sleep, stress, age, medication, geography, and daily routine. It works alongside the pancreas, liver, brain, fat tissue, muscle, thyroid, immune system, and nervous system. This makes metabolism feel less like a sealed machine and more like a living environment. Human cells digest and absorb. Microbes ferment and modify. The liver sorts the results. The immune system watches the border. The brain receives signals from the gut through hormones, nerves, and circulating molecules. Energy use is shaped by this quiet cooperation. It is also shaped by time. The same body does not handle energy in exactly the same way at 8 days old, 15 years old, 40 years old, or 80 years old. Growth, hormones, tissue repair, muscle, organs, and aging all change the cost of being alive. Across a lifetime, the cost of staying alive keeps changing. A newborn does not use energy like an adult. A teenager does not use energy like an older person. A pregnant body, a nursing body, and a body moving through menopause all carry different demands. The clearest picture of this came from a large study of daily energy use across the human lifespan. Researchers looked at people from 8 days old to 95 years old. They used a method called doubly labeled water, which tracks energy use in real life by following harmless forms of hydrogen and oxygen as they leave the body. That method matters because metabolism can look different in a laboratory chair than it does during ordinary days of eating, sleeping, walking, working, and resting. The results challenged a common belief. Many people imagine metabolism dropping sharply in early adulthood, as if the body suddenly changes in the 20s or 30s. After adjusting for body size and composition, the pattern looked more gradual and more specific. Infancy stood out first. A baby's body is small, but its energy demand is intense. By about 1 year of age, energy use adjusted for body size can be far higher than an adult's. That makes sense when the body is building itself quickly. An infant's brain is growing, bones are lengthening, organs are maturing. The immune system is learning the outside world. New tissue has to be made from milk, oxygen, minerals, amino acids, fats, and sugars. A baby also has a large surface area compared with body weight, which makes temperature control more demanding. Warmth, growth, digestion, and brain development all ask for energy at once. Childhood slowly changes that pattern. As growth continues, the body still needs energy for building tissue, repairing cells, and supporting activity. By adolescence, hormones rise and body composition shifts. Muscle, bone, blood volume, reproductive tissues, and height can change quickly. Growth spurts may add several centimeters in a year. The body is still building, but it is moving toward adult proportions. By around age 20, adjusted energy expenditure tends to settle closer to adult levels. Through much of adulthood, metabolism appears more stable than many people assume, once size and body composition are taken into account. A person at 35 may feel different from the way they felt at 20. Sleep may be shorter. Work may involve more sitting. Stress may be higher. Muscle may slowly decline if it is not used regularly. Meals, alcohol, medication, pain, pregnancy history, and daily movement can all change. Those life changes can affect body weight and energy use, even when the underlying resting metabolism has not collapsed in a sudden way. Pregnancy creates its own metabolic state. The body builds the placenta, expands blood volume, supports the growing fetus, and changes how it stores and releases fuel. During lactation, milk production also carries an energy cost. Human milk contains fat, lactose, proteins, minerals, immune factors, and water, all made or moved by the parent's body. These states show how metabolism responds to biological purpose. It rises when the body is building and feeding another human life. Menopause adds another kind of transition. As estrogen levels change, many people notice shifts in fat distribution, sleep, appetite, body temperature, and muscle maintenance. More fat may collect around the abdomen. Sleep disruption can affect hunger and energy regulation. Aging muscle may become harder to maintain without enough movement and protein. Menopause deserves a careful explanation because the body is changing across several systems at once. It should not be reduced to a simple claim that metabolism stops. Later in life, energy use often declines more clearly. After about age 60, adjusted expenditure tends to fall gradually. Several causes can overlap. Lean mass may decrease. Organs may change in size or function. Physical activity often becomes lower. Inflammation can rise. Cells may repair damage less efficiently. Mitochondria may become less effective in some tissues. Sleep can become lighter and more broken. None of these changes acts alone. They gather slowly, like many small adjustments across years. This is why age and metabolism are connected. But the connection is more detailed than a single slowdown. Early life spends energy on rapid construction. Adult life often holds a steadier pattern than expected. Older age brings gradual changes in tissue, movement, hormones, and repair. These patterns were measured because scientists found ways to follow the body's invisible energy use outside the walls of a lab. The body's energy use leaves traces. Some traces are warmth. Some are breath. Some are chemical markers moving quietly through water, blood, urine, and carbon dioxide. Long before wearable watches and phone apps, scientists tried to measure metabolism by measuring heat itself. This method is called direct calorimetry. Calorimetry comes from calorie, a unit of heat energy. In direct calorimetry, a person or animal stays inside a carefully built chamber, and instruments measure how much heat leaves the body. The idea is simple and physical. When cells process fuel, some of the energy becomes ATP, and some spreads as warmth. That warmth moves from the skin into the surrounding air and walls. A direct calorimeter tries to capture that heat and turn it into a measurement. These rooms had to be built with great care. Airflow, wall temperature, humidity, water pipes, and insulation all mattered. A small error in heat loss could blur the result. Direct calorimetry was powerful, but it was difficult, expensive, and not easy to use for ordinary daily life. A second method follows the breath. This is called indirect calorimetry. Instead of measuring heat directly, it estimates energy use from oxygen consumed and carbon dioxide produced. That works because fuel oxidation depends on oxygen. When mitochondria process carbohydrate or fat, oxygen helps accept electrons near the end of the electron transport chain. Carbon atoms from fuel leave the body mostly as carbon dioxide. A person may breathe through a mask, mouthpiece, hood, or room system. The instrument measures how much oxygen disappears from the inhaled air and how much carbon dioxide appears in the exhaled air. From those two numbers, scientists can estimate energy expenditure. This is why a resting metabolic rate test often involves lying quietly while breathing through equipment. The person may rest in a calm room, avoid recent exercise, and arrive after several hours without food. The goal is to measure the body near a resting state, when digestion, movement, stress, and temperature are controlled as much as possible. Breath can also reveal the fuel mixture being used. The respiratory exchange ratio compares carbon dioxide output with oxygen intake. When the body is using mostly carbohydrate, the ratio moves closer to 1.0. When the body is using mostly fat, the ratio moves closer to 0.7. Real bodies often sit somewhere between those values because they use a mixture of fuels. A person after a high carbohydrate meal may show a different pattern than the same person after an overnight fast. During exercise, the number can shift again as intensity rises and muscles draw more heavily on fast fuel. Metabolic chambers take indirect calorimetry and expand it into a room. A person can sleep, eat, sit, walk lightly, or use a small treadmill or cycle inside a controlled space. Air entering and leaving the chamber is measured across many hours. This lets researchers watch energy use across a whole day, including sleeping metabolism, meal effects, and small movements. The chamber is still artificial though. People may behave differently when every meal, step, and breath happens inside a research room. For ordinary life, scientists use a quieter method called doubly labeled water. This method uses stable isotopes, which are harmless heavier forms of atoms. The water contains deuterium, a heavier form of hydrogen, and oxygen-18, a heavier form of oxygen. A person drinks a measured dose. Over the following days, deuterium leaves the body mostly in water. Oxygen-18 leaves in water and in carbon dioxide. By comparing how quickly the two labels disappear, researchers can estimate how much carbon dioxide the body produced. Carbon dioxide production then gives a way to estimate total energy use while the person lives normally. They can walk to work, sleep in their own bed, eat regular meals, care for children, climb stairs, sit at a desk, or move through a city. This is why doubly labeled water has become so important for measuring free living metabolism. It helped reveal energy patterns across age, body size, sex, pregnancy, lactation, and daily activity outside the lab. The invisible burn became something that could be followed across real days. That measurement also made exercise more interesting. When scientists measure bodies outside controlled rooms, movement clearly matters, but the body's response is more layered than a simple number on a treadmill screen. A treadmill screen can make energy use look exact. It may show a number after 20 minutes of walking, cycling, rowing, or climbing. That number can be useful, but the body's response to exercise continues beyond the machine. Muscle contraction begins with ATP. Every time a muscle fiber shortens, tiny protein filaments inside it slide past each other. Those filaments are called actin and myosin. Myosin heads pull on actin, release, reset, and pull again. Each small pull uses ATP. A walking step, a push-up, a swim stroke, a bicycle pedal turn, and a slow lift from a chair all depend on that same basic chemistry. Muscles store a little ATP directly, but only enough for a very short time. They have to keep remaking it as movement continues. For quick, hard effort, carbohydrate becomes especially important. Glucose can be drawn from the blood, and glycogen can be drawn from storage inside the working muscle. Muscle glycogen is local fuel. The glycogen stored in the calf helps the calf. The glycogen stored in the thigh helps the thigh. During sprinting, heavy lifting, fast cycling, or climbing stairs quickly, muscles need energy at a high rate. Carbohydrate pathways can supply that energy faster than fat pathways. During longer, lower intensity movement, fatty acids often contribute a larger share of the fuel mixture. A long walk, an easy bike ride, a steady hike, or a relaxed swim may use more fat proportionally than a short sprint. That does not make lower intensity movement a special shortcut. Total energy use still depends on body size, duration, intensity, fitness, temperature, terrain, and how the person moves afterward. The phrase fat burning zone captures one real detail and leaves out several others. At a gentler pace, a higher percentage of energy may come from fat. At a harder pace, the body may use more total energy overall, even if the percentage from fat is lower. The body cares about the full day, not just the fuel mixture during one narrow window. After exercise, oxygen use can remain elevated for a while. This is called excess post-exercise oxygen consumption, often shortened to EPOC. It reflects recovery work. The body restores oxygen levels in blood and muscle. It cools itself. It helps rebuild phosphocreatine, a quick energy reserve inside muscle. It clears and reuses lactate. It repairs small amounts of tissue stress and returns heart rate, breathing, and temperature toward baseline. EPOC is real, especially after harder exercise. Popular claims often make it sound larger than it usually is. For many ordinary workouts, the afterburn is a modest addition, rather than a giant hidden furnace. Muscle mass also matters in a measured way. Muscle tissue uses more energy at rest than fat tissue. A person with more muscle usually has more resting tissue to maintain, more glycogen storage space, and more ability to move powerfully. Strength training can help preserve muscle during aging and weight loss. It can also improve function, balance, posture, glucose handling, and daily independence. Still, adding muscle changes resting metabolism gradually. A few pounds of new muscle will not transform the body's daily burn overnight. Its value is steady and structural. It supports movement across months and years. The body can also compensate after exercise. Someone who runs in the morning may feel hungrier later. A person who finishes a hard workout may sit more still for the rest of the day. Background movement can fall without much awareness. The body may become more efficient at a repeated activity, so the same route or workout costs less energy than it did at first. This efficiency is useful. A trained heart pumps more effectively. Muscles coordinate better. Mitochondria can improve their ability to process fuel. Joints and tendons learn familiar patterns. From the body's view, wasting less energy on a repeated task is a success. For body weight, that same efficiency can make the math feel less simple. Exercise still matters deeply. It changes muscle, blood vessels, insulin sensitivity, bone strength, mood, sleep pressure, heart function, and the ability to use fuel. It also enters a living system that adjusts appetite, rest, movement, and efficiency around it. Energy use is shaped by motion, recovery, and compensation. It is also shaped by timing, because the same meal, workout, or rest period can land differently depending on the body's internal clock. A meal eaten in the morning does not always land in the same body state as the same meal eaten late at night. The food may contain the same glucose, amino acids, fatty acids, fiber, water, and minerals. The digestive tract may use the same enzymes. The liver may receive nutrients through the same portal vein. Still, the body's timing system changes the background conditions. Human metabolism follows circadian rhythms. A circadian rhythm is an internal cycle that runs close to 24 hours. The word circadian comes from Latin roots meaning about a day. These rhythms help coordinate sleep, body temperature, hormone release, digestion, alertness, and fuel handling. The central timing structure sits deep in the brain. It is called the suprachiasmatic nucleus. The name is long, but its location is the clue. It sits above the optic chiasm, the place where signals from the eyes cross on their way into the brain. Special light-sensitive cells in the eyes send information about morning light, evening darkness, and artificial light to this clock region. From there, the body adjusts its daily rhythm. Morning light helps set the timing of alertness. Evening darkness helps prepare the nightly rise of melatonin, a hormone linked with sleep timing. This central clock does not work alone. The liver, pancreas, skeletal muscle, fat tissue, gut, and heart have clock-related gene activity. A gene is a stretch of biological instructions, and clock genes help cells change their activity across the day. Liver cells may handle glucose differently depending on time. Pancreatic cells may release insulin in a rhythm-shaped environment. Muscle cells may shift how they take up and store fuel. Fat cells may change how strongly they respond to signals for storage or release. This means metabolism is partly scheduled. Insulin sensitivity can vary across the day. Insulin sensitivity means how strongly cells respond to insulin's message. When cells are more insulin sensitive, glucose can move from blood into tissues more effectively. In many people, glucose handling tends to be better earlier in the day than very late at night, though work schedules, sleep, meals, genetics, and health conditions can change the pattern. This is one reason late meals can affect some bodies differently than earlier meals. The calories may be the same, while the hormonal and clock setting around them has shifted. Sleep affects those signals too. A short night can change hunger the following day. Ghrelin, the stomach-linked signal that often rises before meals, may increase after poor sleep in some studies. Leptin, the stored energy signal from fat cells, may fall or become less effective in certain sleep loss conditions. Cortisol, a hormone made by the adrenal glands, follows a daily rhythm as well. It usually rises toward morning, helping the body wake and mobilize fuel. Poor sleep, stress, and irregular schedules can disturb that pattern. Glucose regulation can also worsen after sleep restriction, because the body may respond less smoothly to insulin. These effects do not mean one bad night permanently changes metabolism. They show that sleep is part of the system. During normal sleep, body temperature usually falls. Heat production, blood flow near the skin, and hormone timing all help the body move into its nightly state. Digestion tends to slow compared with active daytime hours. The brain remains active, especially during dreaming, but the body's movement drops. Muscles relax. breathing becomes steadier. Heart rate often lowers. Energy use continues, while the pattern becomes quieter and more regulated. Overnight fasting belongs to this rhythm. Dinner is absorbed over several hours. Later, insulin tends to fall. The liver releases glucose from glycogen. Fat release becomes easier. By morning, the body has spent the night shifting gently from fed state processing towards stored fuel use. This happens without drama in a healthy body. The nightly fast is one of the most familiar metabolic transitions humans experience. Modern life can blur these rhythms. Bright screens late at night, shift work, irregular meals, jet lag, short sleep, and late caffeine can push the body's timing signals out of alignment. A nurse on night shifts, a parent waking with an infant, a student sleeping at uneven hours, or a traveler crossing time zones may all feel metabolism and appetite change with the clock. Timing does not replace food, movement, hormones, or body composition. It gives them a daily pattern. Once energy use is seen through organs, tissue, fuel, movement, sleep, and circadian timing, some differences begin to look clearly biological. Specific hormones, medicines, and medical conditions can shift the system in stronger ways than ordinary daily variation. A clear example begins in the lower front of the neck. The thyroid gland is small, often weighing only about 20 to 30 grams in an adult, yet its hormones reach through much of the body. It makes thyroxine, called T4, and triiodothyronine, called T3. These hormones help influence oxygen use, heat production, heart rate, digestion, and the pace at which many cells carry out their work. When thyroid hormone activity is too low, the condition is called hypothyroidism. The body's energy use can decrease. A person may feel unusually tired, cold, slowed down, constipated, or heavy in a way that does not match ordinary fatigue. Skin can become dry. Heart rate may be lower. Some weight gain can happen, often partly from salt and water changes, as well as shifts in energy use. Hypothyroidism shows that metabolism can truly be altered by a specific hormone system. The opposite condition is hyperthyroidism. In hyperthyroidism, thyroid hormone activity is too high. Many cells receive a stronger signal to spend energy. The heart may beat faster. Hands may tremble. Heat can feel harder to tolerate. Sleep may become lighter or more restless. A person may lose weight despite eating more because the body's fuel use has risen. These symptoms can overlap with other conditions, so they belong in medical care, with blood tests and a clinician's judgment. They still show the larger point clearly. A hormone made by a gland small enough to fit in the palm of a hand can change the body's whole energy pattern. Cortisol adds another kind of disruption. Cortisol is made by the adrenal glands, which sit like small caps above the kidneys. It helps the body respond to stress, maintain blood pressure, regulate inflammation, and manage fuel availability. In Cushing's syndrome, the body is exposed to too much cortisol for too long. That can happen because of certain tumors or because of long-term treatment with steroid medicines in some medical situations. Prolonged high cortisol can affect fat distribution, muscle tissue, blood sugar, skin, bones, and blood pressure. Fat may collect more around the trunk, neck, or face. Muscle can weaken. Blood glucose may rise because cortisol encourages the body to make and release more fuel. This is metabolism being shifted by a clear chemical signal, not by a vague broken engine. Insulin-related conditions can also change how the body stores and uses fuel. In insulin resistance, cells respond less strongly to insulin's message. The pancreas may need to release more insulin to help move glucose out of the blood. Over time, this can affect hunger, fat storage, liver fat, blood sugar, and energy balance. PCOS, which stands for polycystic ovary syndrome, can involve insulin resistance in some people, along with changes in reproductive hormones, menstrual cycles, skin, hair growth, and body composition. It is a real biological condition, though it varies widely from person to person. Medications can influence metabolism too. Some medicines can increase appetite. Some can cause fluid retention. Others may affect sleep, fatigue, blood glucose, thyroid function, or body weight. Steroid medicines, some antidepressants, some antipsychotic medicines, insulin, and certain seizure medications are examples often discussed in medical settings. The effect depends on the dose, the person, the reason for treatment, and the other systems involved. Rare genetic pathways show how powerful appetite and energy regulation can be. Leptin signaling is one example. Melanocortin signaling is another. The melanocortin-4 receptor, often written as MC4R in medical language, helps the brain regulate appetite and energy balance. Rare changes in this pathway can make hunger much stronger and weight regulation much harder. These rare cases do not explain most ordinary differences between people, but they prove that body weight and metabolism are deeply connected to brain signals. All of these examples deserve careful framing. A person cannot diagnose thyroid disease, Cushing's syndrome, PCOS, insulin resistance, or a genetic condition from a feeling alone. Symptoms can have many causes. Medical testing, history, and professional care matter. Still, these conditions show that metabolism can be genuinely disrupted in specific ways. Hormones can change fuel use. Medicines can shift appetite or water balance. Genetic pathways can alter hunger. Sleep, stress, illness, and inflammation can change how tissues respond. After all these layers, the phrase fast or slow metabolism can finally be understood with more care. The body's burn comes from many connected systems, and each one adds another reason two bodies may store and use energy differently. The phrase fast or slow metabolism now has more shape around it. It is a useful shorthand with limits. It points toward real differences between bodies, while leaving out the many systems that create those differences. A body begins handling energy before food ever becomes body fat. Teeth, saliva, stomach acid, pancreatic enzymes, bile, villi, and microvilli turn a meal into smaller pieces. Carbohydrates become simple sugars such as glucose. Proteins become amino acids. Fats become fatty acids and glycerol. Those pieces enter blood, lymph, liver, muscle, and fat tissue, where hormones help decide their path. Insulin rises after many meals and helps move glucose into cells. Some glucose becomes glycogen in the liver and muscles. Some incoming fat can be stored as triglycerides inside adipocytes. When food fades from the bloodstream, the pattern changes. Lower insulin makes stored fat easier to reach. Enzymes inside fat cells split triglycerides apart through lipolysis. Fatty acids travel through the blood attached to albumin. Glycerol can return to the liver and help make glucose. The stored fuel still needs mitochondria before it becomes usable energy. Inside cells, fatty acids are broken down through beta oxidation. Their carbon pieces move into the citric acid cycle. Electrons pass through the mitochondrial inner membrane. Oxygen helps complete the chain. Carbon dioxide leaves through the breath. Water is formed. Heat spreads through tissue. ATP carries usable energy into muscle contraction, nerve signaling, repair, transport, and thousands of smaller tasks. This work is uneven across the body. The brain, liver, heart, and kidneys spend a large share of resting energy, even though they make up a small share of total body weight. Muscle matters because there is so much of it. Fat tissue matters because it stores fuel, releases fuel, cushions organs, insulates the body, and sends chemical signals. A larger body usually has more total tissue to maintain. A body with more fat-free mass often has a higher resting energy need. Even similar-looking bodies can differ through organ size, thyroid hormones, nervous system tone, inherited pathways, and the way cells handle energy. Daily movement adds another layer. NEAT, the energy spent outside sleep, eating, and planned exercise, can change the whole day. A person may stand, pace, gesture, clean, shift posture, climb stairs, or tap a foot without thinking of those motions as metabolism. The body counts them anyway. Fat tissue also speaks to the brain. Leptin carries information about stored energy. Ghrelin rises from the stomach before many meals. GLP-1 and peptide YY come from the gut after eating. The hypothalamus reads many of these signals while also helping regulate hunger, temperature, hormones, and energy balance. During fasting, the body shifts from recent food toward liver glycogen, fat release, gluconeogenesis, and, over longer periods, ketone production. When scarcity lasts, adaptive thermogenesis can lower energy use beyond the change expected from a smaller body alone. The body may reduce heat production, spontaneous movement, heart rate, thyroid activity, and other costs. This response can feel frustrating in modern life, but its older purpose is protection. Adipose tissue itself has more than one form. White fat stores long-term energy. Subcutaneous fat lies under the skin. Visceral fat sits deeper around abdominal organs. Brown fat and beige fat can spend fuel as heat through UCP1, a protein that lets mitochondria release more energy as warmth. The gut microbiome adds quiet chemistry of its own, fermenting fibers into short-chain fatty acids, such as acetate, propionate, and butyrate. Age changes the pattern again. Infancy spends energy on rapid growth. Much of adulthood is steadier than many people assume after body size and composition are considered. Later life brings changes in lean tissue, organs, repair, hormones, sleep, and activity. Scientists measure these patterns through heat, breath, metabolic chambers, and doubly labeled water, following oxygen, carbon dioxide, and harmless isotopes through real human days. Exercise changes fuel use, muscle, glucose handling, recovery, and fitness. Sleep and circadian rhythm shape when the body handles glucose, hunger, temperature, and stored fuel most smoothly. Medical conditions, medications, and rare genetic pathways can shift the system in stronger and more specific ways. So the body's metabolism is active, layered, and adaptive. It stores, it releases, it measures, it protects, it spends. Even in sleep, the work continues softly. The heart keeps its rhythm. The lungs trade oxygen for carbon dioxide. The brain maintains its electrical patterns. The liver steadies the blood. The kidneys sort water, salts, and waste. Cells repair membranes, copy instructions, build proteins, and hold warmth near 37 degrees Celsius. Somewhere in the quiet body, fuel is being moved from one form to another. Some is saved. Some is released. Some becomes heat. Some becomes ATP. And beneath awareness, through the slow hours of the night, metabolism keeps deciding what to store, what to use, what to repair, and what to keep alive.